Welcome to the second part of my video on guiding. I'm in my little observatory and I thought I'd take a moment to explain some of the challenges that we try to overcome with auto-guiding. And to give a sense of perspective, I've done a little bit of homework. So I've taken some typical parameters from a mount, not necessarily one like this, but for instance, if you've got a 5 arc-minute polar misalignment, the drift rate is 0.015 arc-seconds per second, so very small. The periodic error of a mount with plus or minus 15 arc-seconds of movement over maybe something like 6 or 7 minutes would have a maximum drift rate or a tracking error rate of about 0.15 arc-seconds per second, so 10 times bigger. And lastly, seeing conditions. Seeing conditions can change from 1 second to the next, and they can change up to 1.5 to maybe even 3 arc-seconds per second, so 10 times bigger again. And this highlights the challenge that we have, in so much that what we're trying to do is look at tracking errors and periodic errors, but not react to seeing conditions, which can be an order of magnitude higher. So that's one side of the coin, and the other side of the coin is when we start to move a mount, it doesn't necessarily move in the way we want. And no matter how good we make the mount polar alignment or its periodic error, we still have seeing conditions to contend with. So what happens in a lot of cases, amateurs overreact to the seeing conditions that are measured by the autoguider and thrash the mount about trying to fix it, but of course they're too late. And so what we actually do is make matters worse. So for instance, on this little telescope here, very short focal length, I have a guide scope mounted to the top. It's very securely mounted with guide rings that can't wobble, and very importantly the focus tube has a proper lock ring that locks the tube absolutely securely. I try to avoid the helicoid focuses because the lock screw on them doesn't actually lock the mechanism, it just simply locks it from turning, but you can wag the guide camera around like a puppy tail, which isn't very good. So the most important thing before we start out is that the camera and the guide camera and their optics are as rigid as possible and have the least amount of flexure as possible. So this particular telescope mount is pretty good. It has very low periodic error, about 1 arc-second per over about an 8-minute period, and its polar alignment is less than 30 arc-seconds as well, so very good indeed. And you might think, well, why do you need guiding, especially since it allegedly has something called ProTrack, which can adapt for conditions in the sky, like for refractive indexes and certain amounts of flexures. And to a large extent it can cope, and with a short telephoto lens like this, it's probably good enough. But as you get longer telescopes, it's probably not quite good enough, and you need to think about alternative mechanisms to get your tracking error just right. Because although you can plug in atmospheric conditions like humidity and barometric pressure and temperature, the model that uses that to calculate the effect of the refraction of the atmosphere is not perfect, and so auto-guiding is still something that I use as a fallback. So in the case of a short scope like this, I might do auto-guiding maybe once every 5 or 6 seconds just to keep things on track, whereas with a longer telescope I might have to do it more frequently because the sensitivity of that imaging camera to a tracking error is far greater. So a couple of the mechanical things that we're trying to overcome with our guiding algorithms, first of all, is to not react to seeing, and that's done by a number of methods which include in effect a low-pass filter. So if the real error is 10 times slower than the seeing conditions, even potentially 100 times slower than the seeing conditions, if we filter the results we get from the camera, we can potentially ignore all the high-speed fluctuations of the star position in the guide system and just respond to the underlying trend. And there are a number of algorithms in the guiding programs that do this. Some, for instance, called resist switch, prevent the mount going backwards and forwards, so it knows that there's a trend in a certain direction, and it tries to only make corrections to correct that error trend. There are other ones which simply just take a filtered results. They take lots of guide pulses and they filter the result and only give out an averaged output, which is okay, but you can sometimes run into problems when, with periodic error, the error changes state from being positive to negative, and it takes a while for it to catch up. And there are other simple algorithms which simply just take an exposure, and they use a little bit of the last few guide pulses to kind of flavour what the output is, and we call that hysteresis, which is in effect like a sort of delay. So the mechanical things that we're trying to overcome in a mount change depending what axis we're talking about. So at any angle, when the telescope is pointing at the sky, there are minute flexures in the optics and in the mount and in the focus tube, and so while the mount might be pointing in the right direction, the actual camera can be pointing in a very slightly different direction. And we're talking about arc seconds, bearing in mind that an arc second is a 3,600th of a degree, so a very small amount. You won't see these movements, but you can see it on the image. Next, we need to think about the mechanical attributes of a telescope mount and how we overcome the problems. And the problems are different on the different axes. On the right ascension axis, as it tracks the stars, it's always moving in the same direction, and even with guide pulses going into it, it'll either speed up or slow down, but never change direction. So the gears are always engaged in one direction only, and therefore you tend to get more reliable control and response to a guide pulse on the right ascension axis. On the other axis, the declination axis, this typically is stationary, and the only reason for it to move is to either fix atmospheric refraction effects as the altitude changes, or a drift effect caused by a slight polar misalignment. And in this case, we are potentially reversing the direction of travel of the declination axis. And if there is any play in the gear system or the transmission system, then potentially there's a dead band in which we issue a guide or correction pulse, but nothing actually happens because all it's doing is taking up the slack to reverse the direction. And a number of guider algorithms try to fix this problem by reversing the axis, reversing the controls only when the axis really needs to change direction and it's confirmed after a number of results that it's going in the wrong direction. So very complicated, and each axis and each mount is different. And even between imaging sessions, when I change the telescope or even change between hot and cold conditions, I sometimes may have to use slightly different guider algorithms, or guider settings more likely, so that I get the best results. So one of the problems I have in trying to do this set of videos is that this mount is quite good, and I can't demonstrate some of the problems that you overcome with different guider algorithms. So that's a nice problem. And the other problem is the one you can see above me, which is grey sky, which has been with me for about a month now, and I can't do anything about that. So it's going to take a little while before I get some clear conditions to actually demonstrate the different guider algorithms and how to intelligently alter the attributes like hysteresis, aggression, minimum move, and so on. So bear with me. I think actually it's going to take a third video when I'm actually guiding. And so I'll do this first with an explanation of the guider algorithms without physically imaging, and then I'll do a third video with physical running guide systems and seeing what happens when I alter the parameters. So thanks for watching, and I'm going to go back to the computer now and show you the different guide algorithms. Welcome back. I thought I'd spend a little time looking at the various guiding algorithms within PHD2. If I bring it up, the algorithms are found under the brain setting. And if you look here, you'll see that there are a number of different algorithms for the right ascension and the declination axes. In fact, if you look carefully, there's one less on the declination axis, which is the predictive periodic error correction, which obviously you don't get on a declination axis. So which one do you choose?
Well, that's a really good question. And I thought what I'd do here is summarise the major differences between the way the different algorithms work and how they might be useful with different types of mount, good and bad, and different types of seeing condition, good and bad. Let's start off with hysteresis. This is a very straightforward type of guiding algorithm which uses the error on the last measurement plus the hysteresis parameter, which is a percentage of the recent corrections made. And so in this case, a 10% hysteresis means that the correction would be 10% of recent guiding corrections plus the correction calculated off the last sample. And as usual, an aggressiveness setting which says, well, I'm not going to do the whole of the correction, I'm only going to do 65%. And for a long time, this has been my standard algorithm for both right ascension and declination axes. The reason being is that my mount is well behaved, it doesn't have backlash on declination, and it responds to corrections very well. And this is perhaps the simplest of the corrections themselves. One thing to watch out for, if you set the hysteresis too high, you can actually get it to become unstable, especially if the seeing is particularly bad and the mount is good, and it will tend to overcorrect the mount because of the alternating seeing conditions. So just something to watch out for. On a lot of algorithms, there's also a minimum move. So some mounts do not like moving very tiny amounts. They're normally measured in milliseconds rather than pixels because obviously the mount doesn't know what size pixels or what focal length you're using as a guider. But for instance, you can work backwards. My Meade telescope I had some years ago didn't like anything under 50 milliseconds. So at a guide rate of 0.5, you can kind of work back, and using your pixel scale, you can work out what your minimum move is. But anything less than a tenth of a pixel is a bit chancy, because what you're saying is PHD2 can calculate the pixel error to less than tenth of a pixel. So I would use 0.1 as probably a minimum. Now let's just look at a couple of other algorithms, especially on the dec axis. So there's three here which are very interesting. There's Lowpass, Lowpass 2 and Z filter, which are all low-pass filters of varying descriptions that stop the mount overreacting to seeing conditions, bearing in mind that the seeing conditions between one sample and the next could be as much as an arc second, and it would be a very poor mount that is moving 1 arc second in tracking error, between samples. I have had some, but it is quite rare. There's another one which I'll look at first called resist switch. What resist switch does is it tries to work out which way the declination axis is drifting, and it wants to see at least 3 guider corrections in the opposite direction to which it's been doing before it says, fair enough, I'm going in the wrong direction and I need to change. The drawback is that if it incorrectly establishes the trend, then it potentially can cause a lag of 3 samples before it reacts going the other way. But the idea being that if you have a small amount of polar misalignment, then you typically have a predominant drift in one direction, and this will always correct in the opposite direction and not overcorrect in the other direction because of seeing noise. So it is one to try out if your mount has backlash, because the whole reason for resist switch is to avoid changing the mount direction in declination and getting involved with backlash. But also, if you just want to try and be as conservative as possible and not move the mount in the wrong direction against drift, this also can be used. Again, there's a minimum move, there's an aggression setting, and also there's this little button here called fast switch for large deflections. And as the pop-up shows, it's basically, if it realizes it's gone the wrong way and you get a massive correction saying go in the other direction, it'll override it. So that's quite an interesting one, and I want to now look at the 3 low-pass filter jobs. The first one basically does a very simple median error. So it looks at it's not quite the average, because the average is mean, but it looks at the predominant error that it's seeing on every sample, and it uses that to do the next one. But to avoid it becoming too sluggish, it also tries to establish if there's a trend, and this weighting is how much of that trend that it puts into the calculation. So the idea being that the trend is there if you have drift, and so it tries to use that information to contribute to the error correction. So it tries to be a slow, sluggish filter, but with some intelligence that says, I don't want to be too slow and not catch up with the problem. The algorithm below that, Lowpass 2, although the name's the same or similar, it works in quite a different way. This basically does a slope calculation based on recent corrections, and it's typically used for good mounts and for good seeing conditions, and those sort of mounts which typically have encoders where you don't expect any large errors. The aggression setting again just looks at how much of the predicted error should it use, and as I said, it's for well-behaved systems, but if you have a low-cost mount with typically large periodic error, this is perhaps not the best algorithm. The most interesting one is the Z filter, and this has become one that I've been using predominantly in recent times. It's a fairly recent addition to PHD2, and what Z filter does is it operates in the frequency domain. So what it does is it takes short exposures, so there's less of a lag between the exposure completing, working out a correction and issuing a correction. But what it then does is this exposure factor multiplies up the errors, the individual errors that are measured, so that it, when I say multiplies up, it sort of averages them. So in effect, if I had an exposure of 1 second and an exposure factor of 5, it's the equivalent of having 5-second exposures in terms of the dampening effect. But the clever thing is, it's like a moving average. It's traditionally PHD2 will take an exposure, and during that exposure, which might be 1 to 10 seconds, it will not issue a correction. And then at the end of that exposure, it issues a correction. Here what this is doing, if I use the example of putting 10 in there with a 1 second exposure, it'll be issuing corrections every 1 second, but it will look at the last 10 corrections and average them so that you get immediate responses. You don't have to wait the 10 seconds before it issues any correction, and it reduces the lag. So if you have periodic error which is quite large, this is probably a good one to try out, and maybe use 1 or 2 seconds as the exposure, and maybe 5 or 6 as the exposure factor as a starting point. It doesn't have an aggression setting, but what it does do is it has a minimum move figure, which looks a little bit low at the moment. So I'm going to increase that to 0.1. Now, the thing about the Z filter is that what it does is it gives emphasis in the correction to underlying trends, in other words, low frequency events like periodic error, which cycle normally every 5 to 8 minutes on most mounts, as opposed to seeing conditions, which is a sub 1 second phenomena. So it's quite a useful algorithm, especially when you have poor seeing noise, or you have a periodic error that's changing quite rapidly, but you don't want to be over aggressive as you normally would be and react too much to seeing noise and correct periodic errors some of the time but not all of the time. So some interesting algorithms, and one of the things I've been working out to try and do this video was to try different algorithms with my mount. And one of the problems I have is that my mount is rather good and it doesn't really go bad. So I can't show you what a bad mount is and how to correct for it. I'm going to probably have to find some examples on the web of guiding characteristics that show some problems and how you would best approach them, because trying to throw these different algorithms at my mount, it behaves all the time, so it doesn't really clearly make a distinction between the algorithms and their settings. But there are some general settings that we can look at in terms of aggression and exposure factors, and we'll look at those in a practical in a little moment. Just before leaving this screen, I thought I'd pick out a few differences between right ascension and declination guiding algorithms. So on the declination axis, resist switch is a useful one because it avoids hitting backlash issues. Lowpass is also a good algorithm simply because it doesn't respond quickly to seeing noise, and it responds better to trends, which you'd expect on the declination axis. Hysteresis is a middle ground, and Z-filter equally has a stronger emphasis on slow trends as opposed to fast trends, so that would also equally be a good one for a declination axis. On the right ascension axis, I would not use resist switch because there's no need, because the right ascension axis is always moving in the same direction. The Lowpass 2 is a slope calculation, which is quite good for good mounts and seeing, so I think you can use that for both axes. The hysteresis axis is a bog standard axis. It's actually, if you set hysteresis to 0, it's exactly the same as the maximum DL guiding algorithm. And again, Z-filter is a good one if you want to try and look at trends rather than react to seeing conditions. So I'm going to be using and comparing resist switch on the declination axis and compare that with hysteresis and Z-filter, which are the three that look interesting to me and which I can explain. As I said, not all of guiding algorithms show a distinct difference with my particular mount. The other thing we'll look at is backlash compensation, and again, my mount doesn't have it, but you can measure it and you can put the value in here. So for instance, if I just cancel that for a second, under tools, if you do the guiding assistant, it'll analyze your mount and come up with some backlash figures. When you do that and go back into the brain, you can put in backlash compensation, and you can put a mount in milliseconds of backlash, and you can also set some limits on the actual overall correction will do. The other little thing that's sitting there at the bottom there, which I haven't explained, the deck guide mode, auto, north, south or off. So you can do RA guiding only by just doing that, which is what you would do if you had a single axis mount, for instance. You can also, auto means it will be bidirectional, go north or south. If you know that you have drift in a certain direction, you can force it to do north or south, but be prepared that after a meridian flip you might have to alter that depending on how your guider optics are set up. And it's different between a little refractor with a guide camera stuck on the end and, for instance, an off-axis guider where the camera goes through a mirror and is reflected. So that's something else to consider, and the way you would work out whether to do north or south is simply to take a number of guider exposures with the actual guider disabled. So for instance, let's just, under guiding, just do enable guide output and disable it, let it run, see which way it's drifting, and then because it actually says guide north at the top here and guide east here, you know which way you're doing it. So you can quickly work out which corrections to do, and then it will just simply issue corrections only in one direction. Now the only problem with that approach is if you use dither and the dither goes in the opposite direction, then it'll take some time for the dither to get trended out. So it's something which you would do if you have a particularly poor mount, in my opinion, in which case you wouldn't necessarily be using dither because that will get confused with it. One last thing just to consider, if you're using Z-filter and using short exposures, your graph here will be very jaggedy and it will look like your tracking area is all over the place. Just remember that with short exposures, what PHD2 is measuring is really the seeing noise, and only when you get to 5 seconds or longer do you really start to see the underlying trend. So just bear that in mind, that while the tracking graph is a useful indicator of tracking error, with short exposures, and I would say that is 2 seconds or slower, you're measuring probably more seeing noise than tracking error, and you have to look at it over a longer period of time to see a trend. We return to PHD2 guiding some long exposures, which gives us a chance to see the true guiding performance of what's going on here. Now, what's happening right now, it is pretty good. You can see that the root mean square error for the guiding error is is only 0.39 arc seconds, which is very tiny indeed. And if you look carefully, you can see the guiding corrections of these little red bars on the declination axis and the blue ones on the RA axis. The RA is going backwards and forwards a little bit, and the declination axis is only in one direction and only once maybe every 10 pulses or so. So what we have here is a mount that is tracking well already, maybe has a very tiny amount of drift, and there's no need to go really aggressive. So if you notice, the exposure time is 5 seconds and the aggression is about 70% on both axes with a small amount of hysteresis. Now typically, if I reduce this time to say 1 second, what I would typically then do is reduce the aggression as well. It's safer for me to use a high aggression with a long exposure because I'm more assured that the error is real because it's had time to even out the scene. And on a short exposure, I would do the opposite, which is I'm less certain that I'm actually trying to guide out drift as opposed to seeing conditions. So a couple of little things there. The other thing with the brain is you can't change the guiding algorithm whilst it's guiding. You see it's greyed out. So you actually have to stop guiding in order to change the algorithm. But you can change some of the parameters, the aggression, the hysteresis, minimum move, and so on. And again, here, for instance, I could make it just north, south, or auto. So those are available to you while it's guiding, which is good because if, for instance, I go back to 1 second, or let's say half a second, so it's now going to get very aggressive. You'll notice that this yellow line comes down, as does the signal-to-noise ratio, which is what that refers to. And this will start going up and down a lot more. Now, one of the reasons it's doing that is because I'm actually putting more energy into the mount by trying to guide out seeing. And you now have plus and minus declination guiding, whereas before it was always plus. So what you typically would do is you would knock this back to say something like 30%, and it would stop doing that and settle a little bit and hopefully only guide in one direction. So I'm just going to go back to my 5 seconds and back to 70% on that. Now, a couple other things just to watch out for. On the guiding parameters, under guiding, there's something called star mass detection. If you have two stars quite close together, this tool is designed to stop the guider latching on to the second star, and it will suddenly see a difference in intensity. The problem is, if you have maybe a vapor trail go across your guide star, while it doesn't particularly detract from your a long exposure image, it can make it appear that the star has lost its intensity, and it will, PHD2 will think it's flipped onto another star, and that can stop the acquisition happening, because when the star mass detection says, oh, my star suddenly changed, it causes sequence generator pro to restart. So I typically do not have this enabled unless you have a very dense star field, but typically I don't. The other couple of things is to watch out for, there's a search region, just to make, if you lose the star, for instance, if you stop guiding during image download, you might want to increase that region so that if you have a bit of drift going on, it doesn't suddenly lose the star. And you can also set a minimum star size so that it can't confuse a hot pixel with a real image. But as you can see here, my image is quite diffuse. So a couple other things just to check on. Stop guiding when the mounts lose. Again, if you don't have that enabled, if you do a micro slew, for instance when the centering process is happening, it can cause PHD2 to confuse, and it's better for it to stop and then restart if it ever has to do slewing between targets and so on. And this one here, if I'm using an off-axis guider, I hit reverse. With a straight through refractor, I don't. And the other one here, if you're doing dither, I do fast recenter after calibration or dither. So rather than taking a number of pulses to get back, it overrides the amount of aggression by doing a much quicker recentering of the guide star after a dither by using large pulses either through ST4 or pulse guiding. So that just reduces the delay. Okay, I'm just going to let that continue, and if you notice this got quite agitated here, not too bad all things considered, and then it's smoothed out a little bit now. So I'm going to let this continue for a little while, and then I'm going to look at guiding algorithms. One thing to look out for when you start guiding is to see how well your mount is performing, and also how well polar aligned you are. So one method to do that is to use the Guide Assistant, which you will find under the Tools menu. While the mount is actually guiding, if you hit the Guiding Assistant, it disables the output and then measures the tracking error over as long a time as you want, but typically you do about 2 minutes. So I'm going to come back in 2 minutes' time and we'll review the data. Okay, a couple of minutes have elapsed and some of the results are starting to stabilise. The drift rate on both right ascension and declination is very small, less than 1 arc-second per minute, and the drift limiting exposure, which allows the drift rate not to exceed the minimum move, is about 2 seconds. Now, the other thing to notice is that the polar alignment area is about 0.3 arc minutes, which again is very good value. On the right hand side you can see an indication of the seeing noise, so pretty small. And if I hit stop at this point in time, it will now go and measure the backlash, which is probably the most important parameter of the lot. So while all these drift rates give you an indication of how fast you need to sample, so for instance 2 seconds here, the backlash potentially will tell me that I need to do some fancy algorithm on the declination axis, either using resist switch or maybe to physically put a backlash number into the guiding algorithm. So it's almost done, and when it's done that, some more values will pop up here. So now we see the backlash has been calculated. It says try to keep my exposure times in the range of 2 to 4 seconds, which I was. Minimum move to 0.1, which is easy. Backlash is small, no compensation needed. So that pretty much describes my mount. Well polar aligned, small amount of backlash, and if you look at the backlash graph here, you can see that where the ideal is the white dots and the red are the actual measured, so very, very small indeed. If you didn't have such an ideal result, you potentially would have a backlash number being suggested here, and you'd hit apply and it would change the algorithm, and similarly the minimum move to these two. So I think that's useful for people especially who have a mount that's not performing perfectly, and for others it's a useful confirmation that your mount is performing and behaving itself. I'm going to stop that and it will continue to guide.